Welcome back. Today in this lecture, we are going to learn about the thermodynamic and chemical properties of natural gas. We already learned some other properties, thermophysical properties like density, viscosity, etc. Now, lastly, in this we shall be looking into some of the important thermodynamic properties. What we mean by thermodynamic, as I told you earlier, that these properties are necessary to understand the various processes related to any kind of heat exchange. And then we shall also just have a glimpse of the chemical properties which are important for the processing of the natural gas. So, in this lecture, we shall be looking at these four properties. First is specific heat capacity, then thermal conductivity, reactivity and solubility. First two relate to the thermodynamic property, whereas the last two relate to the chemical property of any substance. Now, specific heat capacity. This perhaps all of you are aware that any kind of substance, whenever we are trying to heat it up, it will undergo some changes, and one of them is that its temperature will start increasing. So, if I am heating it, it will start increasing, and if I am cooling it, it will start decreasing. So, how much heat is needed to change the temperature of a substance? That is important for us because that determines the cost of energy. So, specific heat means that it is the amount of heat energy that is needed to raise the temperature of a particular mass, unit mass of a substance by a unit degree. That means how much amount of heat energy is needed to change by 1 degree per unit mass of the substance. And as I said that in case of natural gas changes, then heat may evolve or heat may be absorbed by the natural gas. And this heat capacity knowledge is needed for designing of the various types of equipment like the intercooler for the multi-stage compressor, and these compressors are needed as I told you in the processing lecture, that needed to compress the outlet natural gas. There are two types of heat capacities. We know that one is the isobaric heat capacity, that means when the heating or cooling is done at constant pressure, and the which is represented by Cp, and another we have the isochoric heat capacity, that is means when the heating or cooling is done at constant volume. And then we define something called specific heat ratio, that is denoted by gamma, and the ratio is the ratio of the specific heat capacity at constant pressure to the specific heat capacity at constant volume. So, if I know Cp and if I know gamma, then I can find the value of Cv. Now, in the literature there are many correlations available to estimate the values of the heat capacities, and again these correlations may change depending on the type of natural gas and depending on the operating conditions. Here I have shown one of the latest correlations proposed by Jharian in 2014, and this correlation is valid for this pressure range and this temperature range. So, these are quite broad ranges of pressure temperature these researchers have considered, and accordingly they put this particular correlation. These correlations, as I told you, are obtained maybe in a semi-empirical manner, and they consider many of the experimental data in the literature. From that, without going into detail of the derivation, we just understand that these are the correlations, and these correlations need not be remembered. They are just available. You should be aware of the sources of the correlation. That is why I have given the thing, given the source. So we should be aware that yes, there are correlations available. Using those correlations, we can estimate the value of the specific heat, and you will find that all these expressions used in the correlation have been given in these equations. So, and there are many parameters involved in this, like A, capital B, R, etc., etc. All these parameters involved, and you see that all these correlations involve the temperature, the pseudo reduced temperature, then the specific gas heat ratio. So all these things are there, and this Cp0 is the ideal gas heat capacity. So all these host of equations associated with the determination of the heat capacity for the natural gas are given in these equations, and then plugging in the appropriate values, you can estimate the specific heat capacity. And the authors have also listed out the values of the various parameters that are associated with this type of correlation. So again, these things will be available to you. You have to select them properly and get these things, get the values. Then we have thermal conductivity of natural gas. In this case also, we know that what is conductivity? Conductivity determines the efficacy of heat transfer by conduction. So how suppose we are heating something at one point in the of the system, then how that heat is getting propagated to the other places around that point. So that is determined by the thermal conductivity, and these are needed in the design of the various natural gas processing to determine the combustion properties, then even sulfur component estimation. Again, there are many correlations available in the literature of natural gas. I have put one of them, which is also reported very recently, and this particular correlation is valid for these pressure and temperature ranges and this specific gravity range. So, and in this case, we can also, this correlation also considers the presence of the acid gases like carbon dioxide about this particular percentage and nitrogen of about this percentage. So this is quite a generalized correlation accounting for the some of the impurities in the natural gas. We have to understand that because the compositions of the natural gas change in a quite broadly, very broadly, so it becomes impossible to make one correlation for everything. And this correlation is given again in these terms. Again, we have some value of this lambda stands for the thermal conductivity, and this actual lambda, actual thermal conductivity, depends on the thermal conductivity at 1 atmosphere, plus these are the various other corrections for any other deviation for different pressures and temperatures. Here we have the pseudo reduced temperature, here we have pseudo reduced pressure, and many other parameters A9, A10, 11, etc. And these again have been given by this, how to find out the thermal conductivity at 1 atmosphere in terms of many other associated thermal conductivities. For each of them again we have many other expressions which we need to use, and ultimately we have, you see that here the authors also proposed some special expressions for the pseudo critical properties. These are not the ones which we learnt in our previous lecture. So these you have to be very careful about, that the definition or the expressions for the mixing rule, this is something like a mixing rule. So these mixing rules may not remain the same for all types of correlations. So in this particular correlation we have to use this particular mixing rule to find out the pseudo critical properties, and these are the pseudo critical properties for the mixture, and they have considered hydrocarbon, nitrogen, carbon dioxide and hydrogen sulfide to find out the pseudo critical pressure and pseudo critical temperature. And then also there is an expression to find out the specific gravity of the hydrocarbons and the mixtures. After plugging in these expressions, and these are the values of the various coefficients involved in the estimation of the thermal conductivity. So, these coefficients have to use properly to get the value of the thermal conductivity. Next, we come to the chemical property, and in that we start with reactivity. Now, why do we need to know reactivity, and what kind of reactions are expected in the natural gas systems? So, in this, first we come to a very prominent reaction, that is due to the presence of water, and as I told you that water may get reacted with some of the components in natural gas, like methane, like carbon dioxide, like ethane, etc., to form hydrate. So, we need to know that what is the rate of reaction of the natural gas with water, and that can lead to the formation of the hydrate. And then natural gas, because it is hydrocarbon, under some suitable temperature pressure, this natural gas, ethane, methane, etc., they can react among themselves in the presence of some kind of metals. Those may catalyze these reactions to form polymers. So, that means some polymerization reactions may occur in the natural gas systems, and these reactions may lead to the heat generation. So, this heat generation may again cause some other property changes and processing changes. So, we need to know the reaction rates, and reaction may also occur with air to form some kind of unstable oxygen compounds that may cause explosion. So, that's also one important thing, that we need to know the any kind of reaction kinetics or reaction rates that might be occurring in the presence of air. And lastly, that there may be carbon dioxide present in the natural gas, which may react with ammonia. Ammonia is now found with the nitrogen and hydrogen. So, if the carbon dioxide reacts with ammonia, then we get some carbamate formation. So, these carbamates are some compounds which are need to be avoided. And then we have this natural gas may also react with the compressor lubricating oils, and that may result in the blockage and damage of the compressor and the other pipelines. So, that is from these angles we need to know what all reactions are possible in a natural gas system, and if we know them, we know their kinetics, then we can take measures to prevent these reactions to happen. Next in this line is the solubility, and we know that natural gas has a very high solubility in water. So, this solubility can say, with the solubility knowledge, we can say that how much natural gas may get lost with the water. So, that is why we need to know the solubility, and to prevent the loss of natural gas through water, again we may take some precautionary measures, and we know that solubility increases with increase in pressure and decreases with increase in temperature. So, accordingly we can adjust the conditions so that we can prevent the too much of solubilization of natural gas in water. So, with this we look at the now references. These are references which will help you to learn more about these properties. Thank you.